Hey everybody, this is Larry. This is day 6 of the July Leetcode Day Challenge. Hit the like button, hit the subscribe button, join me in Discord. Let me know what you think about this poem. So, hope you enjoyed the drawing video. Let me know in the comments where you think it is. And yeah. Sorry I'm a little bit slow and late today. I'm feeling a little bit unwell. It's kind of difficult to even talk right now, which for a YouTube video is kind of almost the minimum requirement. So yeah. Anyway, let's jump right to it then. Today's poem is 209, minimum size subarray sum. Oh, it seems like it's a poem I haven't done before, so let's take a look. There are not many of them, so I always get excited when I do, right? So given an array of positive integer nums and a positive integer target, return the minimum length of a subarray whose sum is greater than or equal to target. If there's no such subarray, return 0 instead. Okay. I think that two immediate dots. The first one, to be honest, it's going to be binary search, maybe. I mean, that's not the way that I would. Just to be clear, a little bit of a spoiler alert, that's not the way I was going to solve it. But I think you can use these, solve it with binary search, and everything will be okay. Right? If you solve it with binary search, and it'll be, maybe it's even a good practice if you haven't done it before, how to do it with binary search. More spoilers if you want to cover your ears, is that you'll do it with prefix sum, and then the idea would be that for each index, figure out how long of a length to get to target, right? And then so for each number or for each index and number, you do a binary search on the length. You do a binary search on the length, and of course that could be n log n with O of n processing and O of n space, right? So you can definitely do that, right? The idea, and maybe even good practice if you did it the other way. Maybe this goes with the theme of what we were talking about yesterday, about exploring new angles and exploring new things, right? The other way that is to think about is a sliding window. The reason why sliding window works is a sort of one is that the core part is greedy, but I want to say that it almost builds off the binary search idea, right? Because the binary search is, okay. Oops. The binary search idea is that, okay, I don't know, it doesn't matter, right? Maybe I add this a little bit, I don't know why I say it like that. But let's say you have some array here, and let's say you're looking at here, right? You're doing some length, and the target is going to be some length, right? But, with the target, it's going to be some length. And the idea with binary search is that with sliding window is that you're building off the previous known ideas, right? Because here, maybe I'll draw it on top of this. So you already know what the answer for this is for some target. So then here you know that it has to be at least up to here because you know that when you subtract this delta, the target is going to be further away, so it has to be at least here. So that means that you can extend it this way, and of course you can, if you go with the binary search idea, you can even do a binary search starting from this length, right? And then just kind of, it won't change your running time or asymptotic running time complexity, but it is in real time. It'll probably save you a couple of operations. Not that much, because binary search is very fast, and it grows in it halves every time. So yeah, it has to be a very long length for that to really matter that much, maybe, but it still adds up, right? But instead of binary search from there, you can just do a regular thing. In fact, I do wonder if there's a yeah, I mean, I don't know. But yeah, sliding window just now extends that to the right, so that you amortize out all the things. And it turns out that because even though binary search gives you log n time, because you amortize out for each index, you only add it to the segment once and then remove it from the segment once. It turns out that additional operation is O of 1 instead of O of n, right? Because naively you could say, oh, if we keep on extending, it'll be O of n, because you can extend all the way to the end. But that's not how the amortization works, and that's why that works. I do wonder if there's a way to kind of do it that way, but I don't know. But anyway, sliding window. You can't really do better than linear time, linear space anyway. It's not even linear space. Sorry, you cannot do better than linear time and constant space. So sliding window is the way we're gonna go. Excuse me, I'm gonna just sneeze real quick. Oh my! Can't get my sinuses are very off today. Okay. What is 4-3? Oh. Okay, so just return the number. Okay. So yeah, so so there are a couple of ways you can kind of structure this. Even though I said it in that other way, I'm not going to actually implement it that way. That's why I'm a little bit hesitant. But yeah, so I like to do it something like, left is 0, 0, but for right in range of n nums, right? And then the best result total is equal to 0, right? And then here total we add it to the sliding window, the window that is sliding. And then if total is greater than or equal to target, best is equal to I guess best as a 0 is kind of weird. Let's do infinity, right? Returning 0 is weird. That's probably why. So best is equal to min best of right minus left is right minus left plus right minus left. No, right minus left should be right. Okay, and then while total is greater than target, left to the 1. Right, and then return best if best is return 0, something like that, right? Yep. Well, maybe not then. Huh. Did I have my states wrong? Probably, I guess. Let's see. Okay, so why is it returning 0? 0, 0, 0. Total. So left. This doesn't increment. So this is just 1, and then now target. Right. So now 0, 2. Oh no, 0, 1. And today everything's a little bit off, I guess. You really. If this is 1. Oh, I need to. I missed the case here, actually, to be honest, but. I need to do that here as well. Or maybe just here, really. I think that simplifies it. But it's still a little bit off. That doesn't change the case. Maybe I'm just off by 1. But because then now, right? Oh yeah, okay. Yeah, don't know why I'm so reluctant, but I thought I had the bounce right. Yeah. So like I said, this is gonna be linear time, constant space. Can't really do better than that. Um, can do better than that if I didn't make a minor mental thing. Usually it's right minus left plus one, but I didn't. I think the thing to if you saw my confusion here, and maybe it wasn't that long, but it's because I didn't define my bounds correctly. And usually I'm a little bit better about it, but maybe today everything is just nifty, right? Iffy, right? So here actually, um, what we should define is that right is inclusive at this point, right? But I didn't define left, and I thought left was exclusive. Oh, sorry. Yeah, X was exclusive, which is why I got the other one. But maybe X is actually inclusive. It's a little bit awkward because left starts at 0, so that I think that maybe I got confused here because this is the formula if they're both inclusive. So that's the thing. Anyway, that's all I have for this one. Let me know what you think. Stay good, stay healthy to good mental health. Hopefully, I get a little bit healthier as well. But yeah, I'll see you later and take care. Bye bye.